Welcome back. The function f is a one-to-one correspondence or a bijection if it is both one-to-one and odd-to. For any set A, the identity function Ia from A to A defined by Ia x equals x for all x in A is a bijective function. Okay? Identity function is a bijective function. Here is a short review of injective and surjective functions. Suppose that f is a function from A to B. To show that f is injective, how do we show that? Show that if fx equals fy for arbitrary xy elements of A with x not y, then x equals y. This is poorly written, but it should say if x is not equal y, then fx not equals fy. Or fx equals fy, then prove that x equals y. Show that f is not injective. To show something is not injective, all you need are two numbers, two elements of set A such that they are distinct but their image is equal. To show that f is surjective, take any arbitrary element y from the right hand side, from your codomain, and find an element x in your domain such that fx equals y. To show that f is not surjective, find a particular y in your codomain such that fx is not y for all x in A. What does that mean? Y is not an image of any x from A. Alright, inverse functions and compositions of functions. Let f be a one-to-one correspondence from the set A to the set B. Okay, that is, it is bijective function. The inverse function of f is the function that assigns to an element B belonging to capital B, that is the codomain, the unique element A in A such that if f of A equals B. The inverse function of f is defined by f -1 written over here. Note, do not confuse f inverse with 1 over f. 1 over f is a different function which may not exist, but f inverse exists for every surjective function. Okay, for every bijective function. So let's see a picture. A is here, set B is here, f is a function from A to B. If f is bijective, then it is both injective and surjective. What does that mean? To be injective, every two distinct elements go to distinct images. To be surjective, every element here is an image of somebody here. So that's fantastic. Start with any element here. Find a pre-image, that is an element who goes to your chosen element. Okay, such that this element is your image, right? B equals. So assign A. That's your definition of F inverse. Why is this well defined? Well, for every B, there is a pre-image because your original F is surjective. For every B, there is a unique pre-image because F is injective. So you see, you need to have a pre-image and you need to have a unique pre-image. All right, so that's how you are able to define F inverse. If F were not bijective, then F inverse would not be a function. A one-to-one correspondence is called invertible because the inverse we just defined is a function. If a function is not a one-to-one correspondence, then it is not invertible. That is, it does not have an inverse function. Explain with an example why a function that is not injective will not have an inverse function, even if it's surjective. So let's draw pictures and understand this, right? So suppose you have a function that is not injective, all right? So this is set A, this is set B. So here let's draw a picture, a small function which is not injective. That is, my function f goes from A to B. How does it go? It takes this element here. It takes this element here. And it takes this element also here. Okay? So notice my function f is surjective. There are two elements here. Both have pre-images. Let me call this B, right? What is the inverse? What are the pre-images? Well, B has two pre-images. B has two pre-images. In other words, the reverse function is confused which way to take B. Should it take it to A1? Should it take it to A2? In other words, the inverse is not well defined. That is why inverse is not a function. All right. The next explanation that is expected of us is the following. Explain why, with an example, why a function that is not surjective will not have an inverse. You don't want to be surjective. You may very well be injective, but what if you are not surjective? So here are two sets, A and B. Okay. So pretend you are injective. That is, distinct pair goes to distinct elements. Okay, so far so good. This is my function f, right? But f should not be surjective. So somebody out here is left out. Okay, say pretend one or two elements are left out. Let's call this element B, the one who is left out. Well, where will the inverse take B to? Nowhere, because B does not have any pre-image. So F inverse is again not defined. This is why not being surjective implies inverse not defined. Not being injective implies inverse is not well defined. So there is no unique pre-image. All right. Composition of two functions. Let G be a function from set A to set B, and let f be a function from the set B to C. The composition of the functions f and g, denoted by FOG, is defined by FOG. A is f of g of A. Composition is like a chain. First evaluate G, and wherever you land, evaluate f on that. Okay. Here is a pictorial representation of this composition. G is a function from A to B. F is a function from B to C. So first G, then F. So you see how we read it. First G, then F. F of G. All right. Take an element A, see where it lands. Take F on that element and see where it lands. That is the composition. So O, composition, is a chain of two functions. Okay. So notice first G, then F, because G was the first function. So if g is the first function, first f then g will not be defined. You see? So just because f of g is defined does not mean g of f is defined. Even if both f of g and g of f are defined, they may not be equal. That is, composition is not commutative. Let's see an example, right? They are asking us to compute f of g and g of f for the following two functions. Okay. F of x equals 3x plus 5. Okay. And g of x equals 2x minus 3. So all this is happening for all x in real numbers. Okay, for all x in real numbers. Okay, now let's compute f o g. Okay, what f o g means is f of g of x. So whoever is closest to x, you compute that first, g of x. Okay, now g of x is 2x minus 3, so f of 2x minus 3. But what does f do to anything that is its argument? Anything. It takes 3 times whatever is inside plus 5. F takes whatever is inside, multiplies by 3 and adds 5. So whatever is inside remains inside. So let's see what happens here. Distribution, 6x minus 9 plus 5. That is 6x minus 4. All right. What about g o f x? That is equal g of f of x. G of, what is f of x? 3x plus 5. Okay. That is equal to. What does g do to anything? Whatever is inside, it multiplies by the argument inside, then subtracts. So, what is the argument inside? 3x plus 5. This is 6x plus 10 minus 3. That is 6x plus 7. So, notice f of g is not equal to g of f. Okay. So let's continue in our next video.